Hello, welcome everybody. Thanks for coming. I know it's the last session of the day. It's been a long day and I appreciate your attendance here. On the stage with me is Igor, the CTO of 7 Bridges Genomics. Today we're going to be talking about security and compliance on a petabyte scale. Igor is going to handle the first part of the talk and I'll come back up for a second. Thank you.
For coming, and I would like to thank Amazon for inviting us to actually share this talk with you. So what you're going to see during this talk and what we actually want to share with you is actually a little bit of background around the unique challenges that we actually faced when we actually had to secure genomics information. At this scale, we're going to walk you through the case study of how we plan to democratize the access to the Cancer Genome Atlas, or so-called TCGA data. And we plan to do this through 7 Bridges Cancer Genomics Cloud platform. And we're also going to go through a couple of deep dives, how we actually managed to leverage AWS to support and secure all this data and how to meet the compliance that's needed in order to actually give people access to the data. So let's first start with why is securing genomics data so hard? There are many reasons, but we actually believe that there are 3 major components to that. First of all is actually that genomics data is big, and it's only getting bigger. At this image behind me, you can actually see that we are in an influx point now, and that as the number of sequencers is growing and the data that's being produced is actually expanding at such a huge pace, and that we only between 2014 and 2018 expect that the production of new NGS data will exceed 2 exabytes. So besides that, genomes are inherently sensitive. They're very personal data, and you cannot really fully anonymize this information with current paradigms. And once it's out there, you can't really take it back. Pretty much the same like with the fingerprints. And besides that, research is highly collaborative and diverse activity. It occurs in large teams, and numerous analytical tools are being used to process this data. And these tools are not being built with either security or scalability in mind. That said, the challenge we are trying to meet here is to enable thousands of researchers that are using hundreds of custom tools to analyze the petabytes of highly sensitive data in a secure and compliant environment. And we're going to walk you now through the case study, how we actually plan to bring the TCGA data to the cloud. So I believe that at least a certain part of you is familiar with what TCGA data is. But just for those of you that are not familiar with it, it's one of the richest and most complete genomics data sets in the world. It contains 34 tumor types from thousands of patients analyzed across the multiple dimensions. Just to mention a few, it's a microRNA data, it's a copy variant data, it's a sequence genomic data. So it's being developed, it's actually being produced in the last 10 years by researchers all across the United States. And so far it costed more than $375 million to produce this data. And we're talking about more than 1.5 petabytes of data. This is expected to grow to 3.5 petabytes just in next year. That said, learning from the data is very challenging. To put it in a perspective, imagine that you want to move 2.5 petabytes to your local storage in case you have a local storage and you have actually a place where you can store such a large amounts of data. It will take you over 23 days to download this data through 10 gigabyte connection. And that's all assuming that you don't have any network glitches and any problem with the storage, which is highly unlikely to happen. And not only that, it costs more than $2 million per year to just store this data. And not only that, this data is actually being replicated across the multiple data centers across the United States, which brings us to much larger sums of money that's being currently spent on just storing the data. And this data, just to get any meaningful results out of that, requires significant computational resources, which means that you also have to transfer that data somewhere in order to process it, and because you have to always bring computation to that data, not the other way around. And collaborating in real time using this structure is very challenging. So to meet this challenge, NCI, NIH actually announced the Cancer Genomic Cloud Pilot, and they're trying to address these difficulties directly. This whole program was initiated by Dr. Howard Varmus in 2013. An announcement was issued in January 2014, and 3 pilots have been awarded in September 2014. It's Broad Institute, Institute for Systems Biology, and 7 British Genomics. So what's our approach to actually democratize this access to TCGA data? So there are a couple of components we like to talk about that. First of all is data. What we're actually trying to do is to immediately, to actually enable researchers to immediately and securely access the petabytes of both open access and control access cancer genomics data. And also, as an NIH trusted partner, 7 British Genomics is able to authorize approved researchers to even access the control access data. And this is the first control access genomic data set on AWS. Also, very important component of that is reproducibility. Because in order to share the results and in order to actually replicate the results across the different groups that are studying this data, you need to be able to actually execute this workflow and always get the same result, which means that basically you always have to do it with the same versions of the tools. And you always have to be able to replicate results, otherwise the research is meaningless. The third component is actually that we're trying to do this through open standards. We are actually enabling the native execution of Docker-based common workflow language, which is slowly becoming the standard in our industry. And that means that you can actually, if you build your pipeline on our platform, you can always move this pipeline to some other platform that also supports these standards, and vice versa. And also, you can integrate with us and actually have a greater level of interoperability by using our API. And all that is actually implemented through our genomics platform. This is just an illustration, just a diagram to show that there are so many components that actually have to scale and work securely in order to meet this challenge. And so how we actually leverage the AWS to support secure and compliant genomics research. So we are going to talk both about security and compliance. They're connected but separate. In a way, you can't really say that if you've built a secure platform that you're actually meeting any compliance, and that you are actually able to talk with the language with other institutions, and that they have a full trust in both your security and processes around that. And vice versa, you can have a compliant platform that has all the standards met, but it doesn't mean that you're actually meeting any security standards that are higher than just basic required by compliance. So let's reflect a little bit about security. We're just going to walk you through our network and data security that we're trying to build on our side. This is what you're going to see is a very simplified system architecture diagram, and we have many more basically environments that are shown here. But I just want to share with you the very controlled data flow that has to happen in order to actually have a secure platform, and that you have to restrict the resources and sharing and data transfer between the various resources and various environments in your platform. For instance, you don't want to really share all the data that's actually secure and basically stored in a production environment, and that's basically personal data necessarily with the processes that are running in our development environment or staging environment, etc. And in order to do that, one of the things that we actually have to do, just a second, actually that you have to secure a network. We are both separating our accounts and have a different level of compliance in our Amazon accounts, but you also want to isolate the network further and actually have separate VPCs for different environments at the same account. And you also want further use control groups and isolate the instances and firewall the instances in order to limit the access to the resources in your network. And also, you want to secure your data and encrypt your data both at rest and in transit. And that basically means that we are leveraging the server-side encryption in S3. And you can also leverage both the key management that's built in and the server-side encryption and Amazon, but we can always integrate with a separate server-side, with separate KMS solutions. And we also leverage extensively EBS encryption, and we encrypt ephemeral storage on our side as well, because all the data, no matter whether it's PHI and control data or not, is resided on encrypted storage on the Amazon instances. And also, we are encrypting all the transit data in transit. We are never sharing the data without unless it's actually being transferred to the encrypted channel. And also, if you want to integrate your own buckets to our platform, you can do so by giving us rights to ACLs and to ACLs on IAM, and actually give us just read access in order to actually share your data with us. And so, moreover, we are not only leveraging that, but we are not sharing the whole buckets with anybody. You never want to share your bucket with all controlled data from all your customers to your instances. You always want to limit the access only to the level that particular process or user has to see. So we always sign the particular Amazon objects that should be actually used on machines that these tools are going to be executed. And we never we never process the data on the instances that they don't have dedicated tenancy. That actually means that in order to process, if you are running your processing on some Amazon instance, you're never sharing the hypervisor with anybody else. This machine is completely under your control, and you have complete physical isolation from the other Amazon users. And we are only using encrypted storage, and we strictly purge the data. That actually means that in between the processing stages, we are removing the data from the disk. And not only that, Amazon also purges the disk at the end when you actually don't want to use this instance anymore. That said, security is nice, but you still have to enable parallel file access at scale. And it's not enough only to actually secure this data. You have to enable users to do the massive processing on such a large data set. And so I would like to share one deep dive on how we actually leverage AWS infrastructure to have a very huge number of instances that are actually accessing the same data set. So what was the challenge? So there is a large number of bioinformatics tasks that require sharing of the intermediary results between the multiple instances. For instance, you have processing stage 1, processing stage 2, but you still want to run them on the multiple instances and still have to share the results between them without actually transferring unnecessary amounts of data between the stages, or just run, of course, you could run this particular task on one instance, but it could last for days or weeks. So the common solution that we used at the beginning was very simple. We used the coordinator instance with NFS server that would basically that would act as a sharing service between the clients that were processing the actual data. So this was great, and it worked nice up until you actually have the 8 clients that were working on the same data. And this was enough for pretty much many tasks, including the whole genome processing. But you couldn't scale further, especially for some population genomics tasks, like the population calling. You couldn't really do it on just 8 workers efficiently. So we actually started thinking about how we could utilize the infrastructure we have to enable the access on the multiple machines. So we actually want to remove the NFS server bandwidth bottleneck. And so we observed how S3 was behaving, and that we didn't see degradation of performance when we were accessing the same data object with the multiple machines. And that means that perhaps you could use that to leverage this infrastructure in order to access this data from the hundreds of machines, both if you're reading this data, and basically also you can store the intermediary data on S3. And perhaps there is no particular degradation if you use the parallel access and parallel transfer. And we had this hypothesis that total read-write speed on a shared S3 object should significantly exceed this, the architecture we have had with NFS server solution on more than 10 workers. So this is just a diagram of how this infrastructure should look like. And it's very simple. So what are the results that we achieved? So this diagram shows you on an x-axis number of compute instances that are accessing the data. And there's the epsilon axis that shows the throughput in megabytes per second. So the actually the blue line shows the reads, total reads with the prefetching on the same data objects that was acting pretty much linearly. And with the green line shows how the parallel writes were behaving on of course, these are not the writes on the same object, but the multiple objects. And the red one is actually particularly interesting. We also implemented local caching, because computational tasks could benefit if you, for instance, download certain blocks of data locally, you could cache it on a local drive, on SSD drive, and actually in a second pass, you could achieve much greater speed because you were no longer relying on your network, but you could actually do the local access and have much greater speeds of access than you had before. That actually means that if you go change your perspective a little bit, if you look at the cumulative worker performance, this epsilon axis now shows the gigabytes per second, that we could achieve much greater speeds than much greater scale than we actually had with the NFS server. So the lines are pretty much the same. And especially, it's interesting that this line shows where NFS server solutions started to break and degrade in speed because the I/O was completely saturated with the network, so we were no longer CPU bound, but I/O bound. But with this kind of solution, we were able to scale on hundreds of instances. And also, moreover, this is not enough because speed is great, but we still have to implement the secure data access, and we had to meet both security and compliance standards with the SBGFS. So the important thing is, as I said, we never actually show the whole S3 bucket. In order to actually users to be, or processes to see the data through the SBGFS, you first go through our file and metadata database service that actually just limits the access and visibility to only the files that this particular task the user should see. Of course, moreover, you can use the SBGFS to mount the data on your side as well, on your local machine. You're not limited only to just worker instances. And of course, in order to meet the many compliance requirements, for instance, HIPAA, you have to keep the audit logs for 7 years, and we aggregate all the logs using the ELK stack, which is basically Logstash, Elasticsearch, and Kibana, where you can inspect your data both through Elasticsearch interface or Kibana interface, depending on what serves the purpose better. That said, it's not only enough to enable the file access, you also have to do the computation of the data. And how we're actually going to do this by using the researcher-contributed tools that can be written in pretty much anything with any standards. So the challenge is that there are more than 10,000 bioinformatics tools, and there are more than 50 tools just using single TCGA marker paper. Moreover, there are various versions of tools and pipelines and this complexity just explodes. So our approach at the beginning, before we switched to different architecture, was to package the EC2 image with a bunch of dependencies so you can just put your tools and that perhaps should work fine. But that was not the case when we hit more than 100 of tools. That became the dependency hell. So what was our approach? So we actually packaged the tools in the Docker image that are going together with a common workflow language wrapper that describes this particular tool. That means that those are the building blocks of the genomic pipeline where you describe the inputs and output of that particular tool and what are the parameters that this tool actually is using. So that means that you could just ship us your Docker container with package dependency, and we can just put it on minimal image on our platform. So This was much easier now for us to actually manage because we don't have to package all the dependencies, and we could just package the minimal images and run this on our platform and build a larger building blocks of the pipelines on a much easier fashion than before. So what are the benefits that we actually saw by using the Docker to deploy these tools? Docker actually enables the solid resource isolation at the container level. And that means that you can limit the visibility of particular Docker image not only to disk space, like with regular Unix jails. You can limit the network access. You can also limit visibility to a Docker image, what namespace of processes it can see. And it also, as I previously said, simplifies deploying and managing tools at scale. So this is not all that simple. There are security risks that are posed by use of Docker. So Docker daemon, first of all, runs under root privileges, which means you could, if you manage to penetrate Docker, you can probably end up with having the root privileges in this particular computational instance. And user can also package unintentionally or intentionally malicious apps. That means that if you include particular tools in your pipeline that are on a marketplace, and that means that somebody could probably do something with your data, export the data, or just monitor a network or see the packages that are running through a network. So if you're not setting the resource management properly, application could do damage outside its container. And how we actually address this? We're trying to address the secure use of Docker containers by first isolating private and public resources. Docker containers shouldn't see more than it should see to actually do the actual job. And moreover, we are also isolating network resources for each container. We firewall the resources at a local container level. And we are always careful with linking containers. And of course, we are aggregating logs for any forensic or audit that we need to do in case something bad happens. And that brings us finally, how we actually, this is great, but how we actually help people collaborate, how you actually help them to work together, because this is all fine. You can isolate the tools, you can isolate the data, but people still need to share the data and do something with it to achieve anything meaningful on top of our platform. So first of all, it's just enabling the secure access. For instance, in this particular case, we are not only enabling users to access their own accounts on the SBG platform, you actually have to integrate with various authentication mechanisms, and you have to live outside your container and outside your world. So we are actually supporting federated authentication and single sign-on. That actually means in practice, in case of TCGA data, you can log in with your NIH account, and you can access the open data, but you can also log in using the ERCommons account and actually have the access to restricted TCGA data on the platform. Of course, we are also auditing the access, and we can only see if somebody tried to access this data and was not authorized. Moreover, dbGaP is actually refreshing the user database every 24 hours. So that means in case we have to be careful about and log out the users if they don't have the access to this particular data every 24 hours. And moreover, so people have to collaborate somehow. So SBG platform provides the isolation of resources on the project level. That means that in case you want to share the files with somebody or share the pipelines with somebody, you can actually embed this in the project. And you can actually limit the access and control the access to your project. You can give just the read rights and just give somebody rights to see what's in the project, see the files, see the pipelines. But you can also enable users to actually work and write on your projects. And this is completely separate from execution, because execution actually spends some resources and can actually spend your money. So that said, we also, in order to just be able to see what's going on in our platform, we are closely monitoring and testing our platforms. So we are doing penetration testing, we are doing strict patch management, and we monitor our platform. And we also aggregate this, as I previously said, the log. We are auditing all the services and all what's going on our platform. And we can always inspect the logs or revise what was going on in case there was any problem with your actual account, or if there was any problem with your access to your data. So to put it all together, in general, what's the interactions? So user can log into our platform, can upload and download the data through a secure channel. You can basically run some tasks and share the data through projects. Our platform is actually managing the execution of these tasks and actual parallelization based on how you actually set up how your pipeline should be executed and how your tools should be executed. The final results are actually living on Amazon S3, and you can access only data and that you actually have privileges to access. And you can always download and interact with this data outside of the AWS or SBG platform if you want. So what are the general lessons that we learned in this particular case? So first of all, you should always isolate resources as much as possible. That means that you shouldn't share any resource file or whatever the resource is unless it's needed for either process or some other users to see. We actually encrypt everything. And if you encrypt the data, it will just make your life much, much easier. You just don't have to think whether you comply to something or not. And you also have to understand what's the actual scale of data. Security and scalability looks very different on a gigabyte level, on a terabyte level, and a petabyte data level. And you should measure everything. You can't really act upon any of these metrics, either whether it's security or scalability, unless you actually measure it. And also, you should leverage the infrastructure. In this particular case, we were able to leverage Amazon S3 and to achieve much higher speeds and much higher scalability than we could by just a very, very simple NFS solution. And moreover, you should always understand the platform you're running on, so you would be able to extract as much as is possible from it. And that said, I would just like to leave you with one thought, that if Amazon was not meeting all the standards that we actually had to meet as well, we wouldn't be able to bring the dbGaP data and meet the dbGaP compliance to meet the HIPAA compliance. And we are in the process of ISO 27001 compliance, and we are also in the process of achieving the FISMA moderate compliance. But without the building blocks that actually Amazon provides, we wouldn't be able to do that. So that said, I would like to give you Angel that's going to say a little bit more about that.
Thank you, Igor. Excuse me. Thank you, Igor. So I'm going to talk about the second header, which is compliance. You just saw a review of security and the technology that enables security and meeting actual controls for data, for compute, for user management. And we're going to talk about what that means in respect to compliance. So when we're talking about compliance, what are we really talking about? We're talking about building trust between separate parties. A compliance certification is actually not so much technical aspects to it, but more of a shared trust model. And in order for any two parties to communicate, they have to agree on the language of that shared trust model. And the language we use for compliance is, of course, compliance frameworks. For ISO 27001, you could do a binary solo out of that, 00101. But for ISO 27001, it provides a framework for general security management within an organization. That includes putting in processes for categorization of data. Is this sensitive data or not? As well as doing an authorization of folks to have access to that data, and what is the recategorization of data over the long term. So when you think of ISOs, this ISO standard, it's really within an organization putting in processes in place. HIPAA, which actually stands for Health Information Portability and Accountability Act, a lot of folks confuse that with Health Information Protection and Accountability Act. That's actually a misnomer. It's portability. Its whole purpose in life was actually to enable transfer of sensitive data across different types of organizations. dbGaP is actually not a compliance framework. It stands for the Database of Genotypes and Phenotypes. It's a repository of sensitive data. But in order to get access to the dbGaP data, you have to fill out a research plan. So That research plan comes with a set of recommendations called the NIH Genomic Data Sharing Policy. And that policy itself is there to protect the individuals who have donated that data under research purposes so that it's not used for other purposes outside of the research application that it was given. So from the bottom, we have within organization security models. The second one was the cross-organization security models. So how do you build trust across organizations? And the third is, again, for the use of the data, make sure it's not being used for nefarious purposes. When we talk about compliance for AWS, I'm sure you've seen pictures like this about shared responsibility. Shared responsibility when it comes to compliance, it means compliance coordination. We talk about security of the cloud separated from security in the cloud. And AWS, as the cloud provider, manages the security and compliance of the cloud. That means facilities, infrastructure, virtualization, API, and service endpoints. And then stacked upon that, our customers, which include partners, build their security and compliance practices on top of what we provide. This means the data security, data provenance, service endpoints, OS network, and what have you. And then I keep pressing the wrong button, sorry about that. The end users can rely on those two other platforms to do their work. But they still have some responsibility in authorizing access to the data they put on a platform. Finally, third-party audits. You aren't compliant on anything until somebody's verified all the way down through the stack that the user is not doing things that they shouldn't be doing with that data, sharing it with folks they shouldn't be sharing it with, using the protocols that are given by their platform provider, and that the platform provider in turn uses the service endpoints of AWS or the infrastructure to make sure that everything on through that entire stack goes along with the rules. Let's take a particular use case here with the three compliance frameworks that we had talked about before. So, sensitive data. Let's assume you have a survey coming from a case report form or something from a clinical trial. You have a patient coming in. AWS provides you infrastructure for securing that data in transit and at rest, and meets the guidelines of ISO internally, giving you something to build your product on top of, and so on and so forth. For HIPAA, we have security controls and service endpoints that allow you to put in HIPAA-eligible applications on top of our infrastructure. The service provider would then take those service endpoints and service features, utilize them in the right way, such as when you have sensitive data, it's encrypted and it's on the restricted set of services. I refer you to the compliance/HIPAA website for more information there. And then the researcher themselves uses what the infrastructure provider has given, what the platform provider has given, and doesn't do things to circumvent the security best practices here. For instance, if you have a case report form and you create this file, this PDF file, and submit it as, first name, last name, social security number, and address, just so you can keep track of who it's from, that actually breaks HIPAA, right, from a user level. So everybody here has some responsibility to meet the particular guideline. All right, so that closes out compliance in a nutshell for the three security frameworks. I'd like to take this back down to the level of you are a researcher, you are somebody who wants to analyze the data at petabyte scale, or alternatively, you are a central IT organization that wants to make these data available at scale to your user base. One of the best ways of doing that on our platform is to leverage platform providers. Having said that, bringing back our model of security and compliance best practice, this stacked set of responsibilities, when you try to integrate other parts of your environment with the platform, there's the understood notion that sometimes you're going to have things outside of that platform. and you take on a larger burden of the security and compliance capabilities. When you do that, you have to be careful not to circumvent anything that was given to you by the platform here. So that in addition to this stacked responsibility model, there's a horizontal responsibility model between different parts of your environment. For the use case, we're going to talk about analyzing the Personal Genome Project data. Personal Genome Project data is started by George Church at Harvard. Folks have been submitting voluntarily their genomic data as well as phenotype information in the public domain. So there's actually no consent forms to sign for this data, so it's an interesting data set to look at. But there's a slight problem with it in that it is not Illumina data. Illumina controls 90% of the sequencing in the world. It's complete genomics data. So you need some set of tools and some platform in order to analyze and transform the data to make it integratable with other resources like the 1,000 genomes. 1,000 genomes actually is 2,500 genomes at this point, so maybe they should think about changing their name. And TCGA, which we had talked about before. So with the platform, you can integrate the complete genomics tool set, do the transformation at scale, and not have to worry about the operations, and then finally start bringing it down into your downstream processing tools. In this case, in this very simple use case, we're going to use the excellent Gemini project or IPython notebook to start inspecting the data that comes out from a population analysis. The types of queries you can do down here and why you would want to do this outside of the platform, because there's a lot of iterative queries over data like this. For instance, with Gemini, you can ask a question like, identify every unknown loss of function variant in my data set. That means it isn't showing up anywhere else in the rest of the population, and there's an interesting phenotype attached to those variants. That might be something as a pharmaceutical provider or as a researcher I might want to tackle as a downstream analysis program. So the strategies to follow here is rely on your platform as much as possible. In this previous slide, right, we could have translated all of the data outside of the platform into something that can go with the complete genomics tools could go straight into an analysis with these other data sets. But why would you do that? Why wouldn't you just install the tools here, custom tools, into the platform itself so that you can utilize the same infrastructure? Other strategies to follow is read the fine manual, please. Too often we find that folks actually don't follow the AWS best practices when they are working on our platform, and it boggles my mind. And third, to make the box checkers happy, so the compliance team, have a checklist. Have an actual to-do item that you're going to use to do these integrations with your platform providers. So for our checklist here, we have AWS security, right? So are you doing the right thing with VPCs? Are you creating security groups that are principle of least practice? Are you encrypting storage, and can you provably do so? Are you protecting your AWS credentials as much as possible? I can't tell you how many times that I've personally had to help our customer base from a GitHub error. Protect platform credentials, right? Platform providers usually give API endpoints, and with that give you authorization tokens. If you somehow lose these credentials out in the wild, you've circumvented the entire security model that you're supposed to be taking advantage of. So it's critical to protect not only AWS security credentials, but also any other credentials associated with working with this data. You should have standard operating procedures for your operating system application updates and management and deployment. Of course, audit logging of activities that are outside of the platform to make sure you maintain that horizontal responsibility. And then data provenance and lifecycle that stack on top of AWS that you're undergoing. So here's a simplified architecture. We have a VPC with a single zone and a security group around a single instance that is launched with an IAM instance profile. For access to 7 bridges, we're going to go and attach an internet gateway and perform operations over HTTPS or SSL, so in transit and going onto our encrypted storage. You can either do that through the internet or through VPC peering. For our dev, we'll use something like packer.io. Since our platform is Docker-based, this is a great tool to also use for your own operations because you can use the same stack and same code and same development process to go into the platform itself as well as your own infrastructure here. And finally, the use of IAM instance profiles allows you to protect the credentials of AWS and other credentials and other sensitive data that you might want to have on the instance at runtime, but you don't want to expose anything outside of that instance. So let's take a quick look at code, because this is a coders conference. This is how I took a quick stab at supplying sensitive data through the user data metadata. Let's zoom in a little bit for the folks in the back for this section for securing the platform provider. Right? This long, wacky string here is the API key that I've encrypted beforehand with the key management service key here. And since I launched this instance with an instance profile, I can do really simple things like use the AWS CLI to decrypt this plain text key and then write it out to disk for my applications to use. I mean, really simple stuff, but there's so many of our customer base that don't do this. They start shifting and SSHing the keys in there, whereas they don't really need to. They don't need to have exposed themselves necessarily, and this is more automatable. This is for the really blind folks, in case you didn't see that. And then on top of that, here we're using a generated random key for the local encrypted storage. I'm sorry I had to punk out here, but this is a blog post in writing. We're starting to develop real information for folks to use in this space for best practices. So how do we do, right, and for our compliance checklist for this very simple example? Well, I think we did a decent job with AWS security, right? With CloudFormation, we can validate that we have a secure VPC, secure security groups, and encrypted storage, all within a checksum process. We protected our AWS credentials by really, putting into our standard operating procedures of deploying applications using IAM instance profiles and managed policies. We protected our platform credentials by leveraging KMS. And we have standard operating procedures for OS and application updates that are standardized across the platform and anything you do within AWS by virtue of using Packer with some DevOps framework behind it, like Ansible. Audit and logging is left up for homework. I mean, that's always particular to a given environment. And data provenance and lifecycle is always use case specific. And that's the problem that's never going to go away. That might be a different platform to use for a global perspective, or leverage the platform that you have and just have standard operating procedures that say we only take data out temporarily and then delete it at hand. And any long-lived data asset goes back into the platform, and that's what we certify as our process. So that's a very simple data provenance and lifecycle standard operating procedure. Enforcing that becomes the rub. So a couple of notes. I'd like to thank everybody here. A couple of notes. Thank Igor for coming. The Cancer Genomics Cloud will provide access to the TCGA as a public data set on AWS. It will be open up to beta users in mid-November, so look forward to that. And if you need more information, see us after the talk. There are other public data sets that we're doing. If there are public data sets of interest, please come contact me later. And if you have any questions, we'll take them now. Do you want to come up in case we have questions? Great.